this video session. My name is Samuel. In this video session, we shall continue our study on logic and truth tables. This is part 4. In this video, we shall look at the exclusive disjunction. When we did logical connectives, we mentioned exclusive disjunction, but we did not do the truth table for it. So we are going to do that in this video session. We shall also look at some definitions. We'll look at a definition of tautology, contradiction, or some textbooks might write a self-contradiction, and also contingency. Then we shall look at a logical equivalence to know whether two statements are logically equivalent or equivalent. All right, please, before you continue this video, it is highly recommended that you start from the beginning in the series, part 1, part 2, part 3, okay, before you continue with this. So when we did logical connectives, that is part 2, we talked of, when we did disjunction, of course, the logical connectives, we talked about negation, we talked about conjunction, we talked about disjunction, we talked about conditional, and then biconditional. Okay, when we talked about disjunction, disjunction could be inclusive disjunction or exclusive disjunction. When we talk about a disjunction, that is or. Okay, it could be inclusive disjunction, and that is when you have it like this symbol, or it could be exclusive disjunction. Exclusive disjunction is when you have it like this symbol, or if you're doing when we do logic gates, okay, application of logic in circuits, switching circuits, okay. Some textbooks will have it as XOR, yeah. So some will have it like this be with an underline, or XOR, okay. Now some other textbooks might use some other different symbols for exclusive disjunction. Now what is the difference here? The difference is that in inclusive disjunction, we note that if you are considering two propositions, the inclusive disjunction is always true, okay, except when both propositions are false. That is the only time the inclusive disjunction is false. Okay, inclusive disjunction is true when it's always true. The only time it is false is when both propositions are false. Okay, this is what I mean here. When we talk of inclusive, let's look at inclusive and compare it with exclusive. Okay, inclusive disjunction is a V, just a lowercase v, and exclusive disjunction is V with a line here, okay, like an underline. So with inclusive disjunction, let's look at the truth tables of this. If we have P, then Q, P, or Q, okay. As usual, I use double lines to do it. And this is two statements. So because it's two statements, it has 4 possibilities. So we have true, 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 false, false, okay, for the first statement, and true, false for the second statement. So with the or, this will be true, this is true, this is true, and this is false. This is for inclusive disjunction. We did this in the second video. Now, but with exclusive disjunction, you have it this way. You have P, Q, P exclusively. Okay, P or Q in the exclusive sense of it. Now, this will be true, true, false, false, and then true, false, true, false. So with the exclusive disjunction, when both are true, it is still false. That's the thing here, okay? Now this is true, and this is false. So the difference is this. With inclusive disjunction, it is only false when both statements are false. Otherwise, it is true. Then with exclusive disjunction, it is false when both statements are either true or false. Otherwise, it is true. So, inclusive disjunction, this is true when both propositions, this is false when both propositions are false. This is false when both propositions are false. Else it is true. Otherwise it is true. Otherwise it is true. Okay? But with exclusive disjunction, this is false. This is false when both propositions are either true or false. Right? When both propositions are either true or false, otherwise it is true. Otherwise it is true. So that is the thing about it. Okay, the next thing we're going to look at now is we have three important things that we want to look at, into. We have three important things that we want to look into, and they are, first one is tautology, second one is contradiction. Some textbooks write it as self-contradiction. And the third one is contingency. Now, when we talk of tautology, it is a statement or it's a proposition that is always true. Always true. So that means that in the truth table, in the final answer, in the truth table, in the final column, you have only truth table value of truths. True. That's all you got in the final answer column. Okay? But for contradiction, it is never true. It is always false. So that means in the truth table for that contradiction, the final answer column, you have truth table values of false. F. For tautology is T. For contradiction is F. Now for contingency is when it is neither tautology nor contradiction. That means you have at least one true and at least one false. You don't have only trues and you don't have only false. Okay, you have at least one true and at least one false. That is for contingency. So let's look at some examples of what I just explained. Tautology is a proposition that is always true. Always true. That means it has only truth table values of t in the column of the final answer. In the column of the final answer. All right. Only truth table values of t in the column of the final answer. That's tautology. Let's look at some examples. Some examples. The first one, let's look at the P or not P. Because this is one statement, one proposition, it has two possibilities. We did that in previous videos. So we have a P, not P, and then we have a P or not P. And usually I like using double lines to differentiate it. That is the way I like doing it. So the two possibilities, one could be true, one could be false. So this is false and true. And because this is or, this is a true and true. So you see it has only true values in the column of the final answer. Has only true values of t. This is a tautology. This statement is a tautology. Assuming you have P to be the sun is shining, then not P, the sun is not shining, or it is not the case that the sun is shining. Those, if you join them with a disjunction, with an inclusive disjunction, the sun is shining, or it is not the case that the sun is shining. Or you might say the sun is shining or the sun is not shining. Then that's the tautology. Because it's either the sun is shining or the sun is not shining, right? So that is a tautology. It's always true. All right, let's do another example. P and Q implies P or R. Here we have three statements, P, Q, and R. So the number of possibilities is 2 cubed, which is 8. All right. Now, we have it P. Let's do it right here. We have a P, Q, R, then when we did logic and truth tables, part 3, you see you do this in order. You do it in order. Okay, let's do the parentheses first. P and Q, then P or R, then P and Q implies P or R. Right? This is a first column, first column, second column, third column, fourth column, fifth column, sixth column. Now, sixth column is fourth column implies fifth column. Like we did this before in previous video. All right, and I want to use double lines as usual to do mine. Now, because this is 8 possibilities, 4 truths, false, true, 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 false, 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 false. And then Q will be true, 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 false, true, true, false, true, true, false, false. And it will be true, false, true, false, true, false, true, false. P and Q, true, true is true, 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 false is false, true and false is false, false and true is false, false and true false, false and false false, false and false false. P or R, true or true is true, true or false is true, true or true is true, true or false is true, false or true is true, false or false is false, false or true is true, false or false is false. And then the conditional statement, if P then Q, okay, this implies this. P implies Q. Remember what we did in this? If the only time it's false is when P is true and Q is false. That's the only time it's false. Otherwise, it's true. Okay. This we are looking at 4 and 5. True, true will give us true. True, true is true. This is false. It's false and true is true. False and true, true. False and true, true. False and false is true. False and true, true. False, false, true. So you see that this is a proposition that is always false. Always false, which means never true. Never true. In the final column, in the column of the final answer, in the column of the final answer, it has only truth table values of F. All right, let's do some examples. The first one, let's look at a P and not P. P and not P. So this will give us what? What would this give us? We have P, not P, P and not P. Then we have true, false. This is false, true. And this will be false, false. So this is a contradiction. Because here, in the final column, is all false. Then number 2, let's look at another example so that we do more truth tables as we're doing this. P implies Q, P if and only if Q, and P if and only if not Q. P if and only if Q, and P if and only if not Q. All right, let's see what this will give us. So we have P, we have Q, we have a P if and only if Q. Then we have, of course, we are not going to come and start doing that. Now, if you follow this step by step, you will get it right. Let's do it step by step. Then the next one is P if and only if. Let's do the parenthesis first. P if and only if not Q. Then P if and only if Q, and P if and only if not Q. And I use double lines in mine. All right, so this is true, true, false, false. And this is true, false, true, false. So the biconditional is only, if it's true, true, or false, false, it's going to be true. Otherwise, it's false. All right, true, true is true, true, false is false, false, true is false, false, false is true. Okay, I missed something here. Do you know what I missed? You know what I missed? I missed the not Q. So I'll have to do it again. So, truth tables, you really have to be careful. You have to be careful so you do it right. You do it right, then you won't have problem. Okay, let's do it again. I have P. It's good you kind of look at whatever you need first. Okay, you need P, you need Q, then you need not Q. P, Q, then not Q. See that? Okay. Then P, if and only if Q, then P, if and only if not Q. This is the way you put it, and you won't have problems on it. Then P, if and only if Q, and P, if and only if not Q. All right. So this is true, true, false, false. This is true, false, true, false. Not Q, this will be false. This is negation of false is true. Negation of true is false. Negation of false is true. All right, so P, if and only if Q, T, T is T, T, F is F, F, T is F, F, F is T. F, if and only if F is T. Then P, if and only if not Q. Remember, this is we are looking at this. This is column 1, column 2, column 3, column 4. Now, column 4 is column 1, if and only if column 2. Then this is column 5. Column 5 is column 1, if and only if column 3. And then column 6 is column 4 and column 5. This is just to simplify it, to break it down. You must not do it, but it's just to break it down. So now this is column 1, if and only if column 3. So T and F, of course, this is biconditional, so this is F. T and T is T, F and F is T, F and T is F. I mean, not and, it's not and, I mean biconditional. Okay, T, if and only if F is F, T, if and only if T is T, F, if and only if F is T, and F, if and only if T is F. Alright, so T and F is F, F and T is F, F and T is F, T and F is F. So this is an example of a contradiction. Yeah. Because the columns, the truth table values in the final column is all false. Logical equivalence is when we look at statements, we construct the truth tables for the statement. If they have the same truth table values, if they have the same values, truth table values in the final answer column, then they are logically equivalent. If not, they are not logically equivalent. I repeat, two statements or two propositions are said to be logically equivalent if they have the same truth table values in their final answer column of their truth tables. Okay, if they have the same values in the final answer column of their truth tables, then they are logically equivalent. If they do not have it, then they are not logically equivalent. There are so many ways of determining whether statements are logically equivalent. The first one is to construct a truth table. That's the first one. Okay. We shall also determine whether statements are logically equivalent using De Morgan's law and using some of the variations in conditional statement. But that will be in subsequent videos. So for this video, okay, we shall do some examples just using truth tables. So we are kind of reviewing truth tables again here. We say that two statements or true propositions are said to be logically equivalent if they have the same values in the final answer column of their truth tables. So if they have the same values in the final answer column of their truth tables, that means they are logically equivalent. Let's say, it is denoted, the symbol for logical, it is denoted by, logical equivalence is denoted, logical equivalence is denoted by, we denoted or represented by, we denote it like this, okay, kind of a double arrow with two lines in between, or some textbooks will denote it like this: three lines, three equal lines, three equal horizontal lines. Yeah, either of these means logical equivalent. All right, we are going to look at some questions here, and this is just the beginning. You know, we're going to talk more about logical equivalence in subsequent videos. So the question is determine whether these statements, now we are still talking about symbolic logic. Later we shall analyze English statement and see. But now we are doing symbolic logic, which means we are representing the statements by symbols. In subsequent videos, we shall write the statement, and then we have to convert those statements, write it in symbolic logic, and then find whether they are logically equivalent or not. But now, you know, we are just going to use symbols right away. Determine whether these statements are logically equivalent. Some textbooks might just say equivalent. So I have 3 questions for tonight before we call it a night. I have 3 questions tonight. Number 1, negation, bracket, negation, parenthesis P, or negation Q, bracket, and P or negation Q. Number 2, P implies Q, implies R, and the other one is, the other statement is P or Q or R. Then number 3, parenthesis, negation, P implies Q, close parenthesis, and negation, Q implies P, close the parenthesis. And the other one is negation P if and only if Q. So we have P, we have Q, we have not Q, then we have P or not Q, then we have negation of P or not Q, then we have again negation of the negation of P or not Q. All right. So what would this is a true, false, false. This is a true, false, true, false. So not Q will be false, true, Then P or not Q, T or F is T, T or T is T, F or F is F, and then F or T is T. Right? You have to be careful here, very careful when you're doing this. Then negation of T is F, negation of T is F, negation of F is T, negation of T is F. So negation of F is T, negation of F is T, negation of T is F, negation of F is T. Now let's look at the second compound statement. This is the first compound statement, first compound proposition. Second compound proposition, P and P or not Q. So we see P or not Q is even here anyway. See, it's even here. Right? This is the final column. But this is even P or not Q. As you can see, it is the same thing. Yeah. But if you want to do it, if you still want to do it, truth table, P, Q, not Q, then P or not Q. This will be true, false, false. This is true, false, false. This is false, true, true. And T or F is T, T or T is T, F or F is F, F or T is T. T, T, F, T. See that? So because they are the same, because they have the same values in the final column answer, they are logically equivalent. Yes. Yes, they are logically equivalent. Yes. All right, let's go ahead and do number 2. For number 2, we have a R and then P or Q or R. So here we have 3 statements. We have P, we have Q, we have R. Well, let's do this first one first. First compound proposition, and this is second compound proposition. Okay. Then we have a P implies Q. Then we have a P implies Q, then implies R. There you go. That's what we got. All right. So we have a true, 4 truths, true, false, 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 false. Then here is true, false, false, true, false, false. Here is true, false, false, true, false, false. All right, P implies Q. This is, of course, this is conditional, so it will only be F if P is T and Q is F. Otherwise, it's going to be T. Okay, TT is T, TF is F, TF again here is F, FT is T here, FT is T, FF is T, and FF is T. Now, we are now looking at this and this, right? So, we are looking at this and this. So, TT here is T, TF here is F, FT is T, FF is T, TT is T, TF is F, TT is T, TF is F. So this is what you got. Now, let's go ahead and do the second compound statement. The second compound statement, now let me do it here. We have P, we have Q, we have R, we have a P or Q, then we have P or Q or R. So true, 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 false, 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 false. Then this is true, true, false, false, true, true, false, false. This is true, false, true, false, true, false, true, false. All right, P or Q, T or T is T, T or T, T, T or F is T, T or F is T, F or T is T, F or T is T, F or F is F, F or F is F. Now, we now do this here, right? Remember, this is, if you call this column 1, column 2, column 3, column 4 means column 1 or column 2, and column 5 means column 4 or column 3. Just be careful when you're doing it, especially when you do this. When you did that implication, you gotta be careful. Right? So T or T is T, T or F is T, T or T is T, T or F is T, T or T is T, T or F is T, F or T is T, F or F is F. So this is what you got. This is what you have. So are they the same? Let's check them again. When you do logical equivalence, you need to check, double check, to make sure. I know the first one is T, T, that's fine. The second one, let's make sure, let's double check. We see no, they are not the same. So that means they are not logically equivalent. That is it, they are not logically equivalent. All right, the third one before we call it a night. We have the first one, negation of P implies Q, and negation of Q implies P. And then the other statement is negation of P if and only if Q. Okay, so we have this P, these two statements, so 4 possibilities. So we have Q. Now we don't have negation of P or negation of Q, so we don't need to worry about that. So let's go ahead and worry about this one. P implies Q. P implies Q. Then negation of P implies Q. Then we leave this guy first. We did the parentheses, then we did the bracket. Let's do the parentheses in this one and do the bracket also. We have a Q implies P. Then negation of Q implies P. Then we now have negation of P implies Q and negation of Q implies P. You just have to do it step by step. You have to do it step by step. So this is the second one. Let's write it here. P, if and only if. All right. Just have to do it step by step. So this is column 1. Yeah. This is column 2. This is column 3. This is column 4. And column 4 is just negation of column 3. That's column 4. This is column 5. Column 6 is negation of column 5. Then column 7 is column 4 and column 6. I just write it so it can guide you to see so that you don't make mistake. Okay, I will use my double lines. So this will be true, false, false. Let me write this bigger so you can see it better. Let me write it bigger so you can see it better. This is a negation of P implies Q and negation of Q implies P. Okay. Now this is true, false, true, false. P implies Q, TT is T, TF is F, FT is T, FF is T. Negation of it, negation of T is F, negation of F is T, negation of T is F, and negation of T is F. Then Q implies P, right? Q implies P. This one is, column 3 is actually 1 implies 2, right? Column 3, you can write it as that this is column 1 implies column 2, and column 5, you can write it as column 2 implies column 1. So T is T, T here is T, FT is T, TF is F, and FF is T. Right? TFTT, TTFT. TT, TFT is T, TF is F, FF is T. Now the negation is negation of T is F, negation of T is F, negation of F is T, negation of T is F. Alright, so now this last one, this is what I'm looking at now. 4, I'm looking at this and this. So that you don't make mistake and look at another column. You might use anything like pencil or pen or marker to know which columns you're looking at so you don't make mistake, okay? So you don't make mistake, okay? Now, I'm looking at column 4 and column 6. So F and F is F, T and F is F, F and T is F, and F and F is F. Now, let's come to the second compound statement. We have a P, we have Q, we have P if and only if Q, and then we have the negation of P if and only if Q. So this is true, true, false, false, and this is true, false, true, false. In biconditional, it is true when both of them are true or both of them are false. Otherwise, it is false. True and true, true, if and only if true is T, this is F, and this is T. The negation of T is F, negation of F is T, negation of F is T, and negation of T. So, both of them are not logically equivalent. They are not. Both of them are not logically equivalent. They are not. Okay? So thank you so much for listening to this presentation. Please watch out for other videos on logic and truth. If you have any questions, feel free to